Morning, Lonnie.
Good morning.
Did you get a chance to look over any of that gravitational wave material?
Yeah, I looked over some of it. The paper was kind of hard to read.
Okay, yeah,
but
you weren't supposed to understand everything about it. So what did you look through? Yeah, we're going to talk about it today, actually. So you mean to understand what it all meant?
yeah, I was trying to look up some words as they threw them out there. I was like, I don't understand what that.
Okay, all right. Well, so actually maybe you could bring them up with us because, I'm sure if you didn't know them, then most of the class members won't know them either. So we can actually maybe come, see if we can understand a little bit more about it, what the relevance is. I mean, I didn't actually expect you to understand a whole lot about it. Mainly just to see it, that it exists, right? It's a first, right? So it's never happened before. We've never detected a gravitational wave. So this is a big deal. And it happened in your life, right? Actually, really kind of early in your life. It doesn't matter how old you are, you're young. Anyways, it just happened 5 years ago. So how old were you when it happened, right? You were a young guy.
Like
That's the first gravitational wave, but in your life, you're going to see something amazing. You're going to see it develop into probably something more powerful, more profound than anything that has been done in astronomy, which is a really exciting idea. This is just the beginning of it. So we're going to talk today about why I believe that, but also, what's happening right now. In fact, I mean, I really, there's just such a wealth of new information available. It's kind of like, it's almost daunting. In fact, there's so much information, but there's new discoveries being made every day, like every day, in gravitational wave observatories. So, all right. Well, did you get the email or did you go to the announcements?
I saw it on the announcements.
Okay. So you're ahead of the curve. You're always here on time. Thank you for that. So actually, maybe I should just make the class a little bit later, but other people have classes after this, and I don't know. This class is supposed to be a discussion, and you and I can have a discussion. I guess the rest of the people will just kind of listen to our discussion. How about that?
Yeah, I'm okay with that.
Okay, all right. Well, let's talk about gravitational wave. I mean, I have a lot to share with you. It's just really, it's exciting material. So anyway, so yeah, okay. So what else is up? Any questions on that quiz, or you did well, I'm sure. The quiz on the attendance. Yeah, it's fine. Huh?
For a piece of cake.
It's basic.
I think I had already seen both of those videos on kilonovas before.
Oh, you had? Oh, yeah. Okay, cool. Good morning, Leona. How are you?
My audio is off.
Oh, no, I hear you. Yeah, I hear you. Did you get the email or did you go to the announcements?
I got a notification on my phone.
I'm sorry, one more time?
I got a notification on my phone.
Oh, you did? Okay, cool. Okay, so notification came. All right. So why don't we just get started then? Because you guys are here and other people will show up or not. We might get Leonie and then we don't get too many other people other than that. So I'll go ahead and I will focus my video here and then say good morning. And actually, just to introduce you to you guys read a little bit about gravitational waves. It's interesting to note that the design of a gravitational wave observatory is pretty similar. In fact, I would say it's the same design as the Michelson-Morley interferometer, which was designed to detect the ether, right? So that failed experiment, I mean, I don't know if it was a fail. It wasn't a fail, it just didn't detect an ether. Good morning, Brandon. And it didn't detect the ether, actually. It was, for 20 years, they looked for the presence of an ether that would allow light to travel and didn't show up. The same design goes into building the interferometer for the LIGO, right? It's two perpendicular beams, and it doesn't matter, what orientation. In fact, it's kind of helpful that the multiple observatories around the Earth have slightly different orientations to allow them to probe the gravitational wave. So they're three-dimensional waves, right? These aren't, actually, you could even say they're four-dimensional waves, but anyway, three-dimensional surfaces that are propagating through space over time. And yeah, anyway, so you guys watch some stuff, but let me just go through some of that material with you and then highlight, why I think this is so exciting. I really believe, I told Lonnie a second ago, that this is the beginning of a new era in astronomy. So astrophysics and astronomy, cosmology, right? Being able to detect gravitational waves is a new way to probe the universe. And up until now, it's been essentially light, although I was actually thinking about it, and I have to say that we were getting a little bit of a signal from neutrino detectors, right? We are very excited about neutrino detectors. So yeah, other than that though, actually that reminds me, that's something that we should probably talk about, like what is going on in the universe. But anyways, did we talk about dark matter? Anybody help me out? Did we talk about dark matter?
Just a little bit. We talked about how the galaxy is like only 5% matter. So
Okay, yeah. But did I talk about what the dark matter might be? I don't know if I ever got into that.
I don't think we got that far.
Okay. So that might be something, trying to figure out like what we're going to do our last few lectures or last few meetings, and that could be interesting. Would you guys be interested in talking more about dark matter and how to detect it and what it is?
Yeah, and I know I've definitely got my curiosities, so I'd like to know.
Okay, well, so I shouldn't say that I actually know what it is, by the way. I can only tell you that we have a hope to be able to detect it. There's some things we know that it's not, so that's actually one of the things that we could talk about, some of the candidates that were first presented. But anyways, let's stick with gravitational waves for today. So you went to the gravitational wave website LIGO, and they actually have some interesting things. But I actually asked you also to read the paper about the first observed, this is directly detected gravitational waves, right? So gravitational waves were inferred back in the 1970s, actually, and I'll ask you to know about that. In fact, the experiment that led to the Nobel Prize in 1990 sometime, 93, 94, was for detection, not detection, but for deduction that there were gravitational waves emanating from a special kind of system. And so we'll talk about that in a minute, but this is direct observation of gravitational wave by the LIGO interferometers. Not just LIGO, there's a couple of, actually LIGO consists of multiple detectors, but in fact now we have more than just LIGO, we have Virgo, and we have other detectors coming online. So anyways, let's take a look at that paper just for fun and see what I actually expect you to know. It's not a whole lot, by the way. So I don't expect you to understand. Lonnie was saying it's difficult to understand. Agreed, absolutely difficult to understand. But this is our paper, and it's the observation of gravitational waves from a binary black hole merger. So you need to know that, right? That the first detected gravitational waves were from the merger of two black holes. And the way that it works is we have LIGO, right? The laser, you need to know that acronym. Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo. So Virgo was actually a part of this collaboration. So this is a separate detector. These are in the United States. This is in Italy, okay? So they observed simultaneously, this is part of the story, right? The sensitivity of these detectors is so incredible. It's actually a funny little thing to talk about. They detect trucks driving down the highway 100 miles away. I mean, that is the kind of vibration that these devices are able to feel. And so you might be thinking, well, yeah, then how do you ever detect a gravitational wave? Because you want to understand something important, okay? So the signal sweeps upward in frequency, blah, 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 from 35 to 250 hertz. By the way, does anybody know the human hearing range? we say it's from, if you're young, by the way, it's better than when you're older. When you get older, you lose some of your high frequency ability. But apparently, anybody musicians here? Musicians or musical?
I play guitar.
What is it?
I play guitar.
Higher than that? Yeah, it is higher than that, definitely. But we can actually hear down to maybe 20 hertz, even though that's not much of a sound. And we hear up to 20,000 hertz, right? So the human hearing range is supposed to be quite a bit bigger than that. And this is just a small range of frequencies that they're probing, right? And then I want you to write this down. The peak gravitational wave strain of 1 × 10⁻21st. So you want to understand what that means, right? This is a tiny number, first of all, 10⁻21, blah, blah, blah. It matches the waveform predicted by general relativity for the in-spiral and merger of a pair of black holes and the ring down of the resulting single black hole. So there's some words here that you're going to need to understand, okay? So number one, let's talk about this strain. So there's a term strain. Stress and strain are terms, by the way, they don't have units, and so they are unitless, but they refer to the way that, like, actually typically, if I talk about strain in an engineering class, it's the amount of deformation of something, how much it moved. I should maybe, you know what, I just realized, let me just, I'm going to show you a picture because this way you can understand. So the word strain is actually typically used in engineering to define how things are stretched or deformed, let's say deformed, by a force exerted on it. But it's actually it's measured in terms of the original length. Okay, so let's see. Nice picture, anybody? There we go, that's it. Okay, so looking for a picture here. So let's go ahead and take a look. I'm looking at Wikipedia, of course. Okay, so there's normal and shear strain. Okay, so it's not a big deal, but there's different ways to exert a force. So one of the ideas is that you're going to exert a force on an object, and it's going to end up changing shape, for example, right? So there's a couple of different versions here. This one happens to be the forces are going to be along the x direction, and the strain would be the amount of stretching that occurs as a result of the forces exerted, right? The strain is a kind of forces. Actually, I could probably draw a better picture than I'm seeing right here. You know what? I think I'm going to just do that because the pictures I see look too complicated. So let's talk about what strain is, okay? So the concept of strain, just to give you an idea, we're talking about when you exert a force on something. Let's make something kind of long, because that's typically one of the ideas that you'll have to deal with. But it has some length, right? And then what I'm going to do is I'm going to attach it on one end to something, right? And then I'm going to pull on it with a force F. I pull on it with a force like this. Now here's a question for you. If the object doesn't move, but I'm pulling on it with a force F, how strong is the force of attachment back here where the rod is, you know, where this material is attached? And if you think about it for a moment, if it's not moving, the net force is 0. And according to Newton, the net force acting on something is what causes the mass to accelerate. So if I pull on one side of an object, but it's attached, I know how strongly the force of attachment is exerted on the object. It happens to be the same strength as the force that I applied. So what happens when you pull on one end of it and attach it is you're stretching it, right? So The strain is what happens to it, right? What happens to it? Well, it actually gets a little bit longer, right? It gets a little bit longer. So the new length is L plus, let's say, delta L, because of that force, right? And so we don't have to worry too much about, what these things are, or the exact equations, but the strain is defined to be the change in the length divided by the original length, right? That's actually what it is. It's unitless. And so what does that mean? It just means it's a measure of how something will deform when you pull on it. So this is one kind of strain. There's another kind of strain that looks a little bit different. For example, let's say you take a rod and you attach it, right? This is a little bit different, but anyways, this time you're going to hang a weight on the end of it, right? It's like a pole or whatever. And so you hang a force like this. And again, if it's not moving, you know that there's an upward force, which is just as strong, which I'm not showing you. Don't worry about that. But what happens is that the shape deforms, right? So the shape deforms and it gets deflected from the original position. We could call that delta L or something, right? It gets deformed by some position. And it depends on the length of the original shape, right? The longer it is, the more that you'll see this deform, right? But again, we would define this as actually, this is really called stress. But anyways, delta L over L is a measure of how it deforms. Okay, so I've shown you that you have these deformations that are occurring as a result of pushing on it or pulling on it with some kind of a force. So now we're just saying the same thing, but what does it mean to be 10 to the minus 21st? 10 to the minus 21st strain, right? What does that mean? It means that the change in the length of the object compared to the original length is 10 to the minus 21st. Okay, so what, right? Well, this is delta L over L. Okay, so what does it mean? How big is delta L? Well, delta L is going to be 10 to the minus 21st times whatever L is. Okay, so what if it was a 1 meter long, right? What would it mean? Then delta L would be 10 to the minus 21st. Well, you might remember that the limits of human measurements are about 10 to the minus 15th. This is beyond human capability. It is not possible to measure this, right? So this is kind of an interesting problem. So you can't make it 1 meter long. So what do? Make it a lot longer. How about 1,000 meters long, right? 1,000 meters. Actually, I'm wrong. It turns out we are measuring things 10 to the minus 18. That's about right. 1,000 meters, if L is 1,000 meters, then delta L becomes 10 to the minus 21st times 10 to the third. Then you get something that's about 10 to the minus 18th meters. Okay, so that might just be the realm of human capability. And that is essentially what they did, right? They got to the very limit of what is possible for human beings, right? So this is incredibly tiny. And up until now, the technology has not existed to be able to measure this, okay? So that's just one single idea that I want you to understand. Why is this so difficult? The effect is incredibly small. Okay, so this is a key part of understanding why, it hasn't been done until now. I mean, 2015 was not that long ago, and the paper was only published in 2016. Okay, so back to our original paper. Let's take a look again at some more words. Okay, so we saw the strain. It matches the waveform. Write that down, waveform. Okay, so what they did, and this is the big thing, right? This is a big deal, is they prepared in advance. They have calculated the way that black holes should merge, what it should look like, right? They have predicted how those black holes, as they spiral around and create gravitational waves, they're going to be losing energy, and the energy of the gravitational waves as it radiates will cause the black holes to merge together, to come together until they eventually merge. So this is called in spiral, right? The process by which the black holes are coming together. As they radiate gravitational waves, they will come together because they're losing energy, and eventually the merger. Now, the final black hole takes a moment to become a single black hole, and that little moment is called the ring down, right? The ring down, the little vibration of the black hole that occurs at the very end. Okay, so the signal was observed, blah 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 blah. Okay, this is actually really, this is very technical. Signal to noise ratio of 24. I don't want to tell you, I do want to tell you, sorry, I want to tell you that the people that are at LIGO are being incredibly careful about the work that they publish. If the signal to noise ratio is not sufficient, they're not publishing the results. So they have many, many more detections, but they're not publishing them because they consider them to be not a high enough standard. Okay, so they're trying to be really stringent in their declaring that there's gravitational waves. And you can see here that the false alarm rate is 1 per 203,000 years. Okay, and this is called 5 sigma. Would you write that down? 5 sigma. So sigma is in statistics the standard deviation. Okay, so actually just to come back a moment, right? So again, these are kind of ideas that you want to maybe just kind of get an idea. So we have 2 black holes that are spiraling around each other, and the concept is incredibly simple to understand. If the masses are very similar, the center of mass is pretty close to the middle. They're going to orbit around the center of mass. They orbit around the center of mass. And what happens is that they have energy, right? The energy of the system is going to decrease over time. But remember, we have 2 different laws: conservation of energy, right? We understand that. So what does it mean? As they radiate gravitational waves, right? As the waves radiate away, they lose energy. And because of that, they have to spiral closer together. They have to lose potential energy, okay? They lose potential and give off gravitational waves. That's conservation of energy. But you also have conservation of angular momentum. So what happens as these 2 spiral closer together? They have to rotate, they have to spiral faster in order to conserve the angular momentum. Okay, so that must be true. They must follow these 2 thoughts. So you're not getting rid of angular momentum though, right? This is an important idea. You're getting rid of energy in the gravitational waves, but as far as I understand, you're not getting rid of angular momentum. There's no way to get rid of the angular momentum. So they must spiral faster as they come together. And then let's talk about the sigma. Sigma is the standard deviation. And you guys may, has anybody taken statistics before? Standard deviation? If you talk about a normal distribution, right? Right, looks something like that, a bell curve. Then about 67%, something like that, 67%. Anybody know the numbers? I forgot the numbers. It's e to the 67%. That's about 1 sigma. Okay, so sigma is a standard deviation, and within 1 standard deviation, I'm a little rusty on this. I have to go derive it, but within 1 standard deviation, I think it's like, I don't know, I want to say 67%. Hold on. Standard deviation. Wikipedia, help me out here. 68%. Okay, here we go. All right, we got a beautiful picture. Might as well just use it. Okay. So this is the Wikipedia article on standard deviation. If you are within, if you take a look right here, plus or minus sigma from the middle value. So the middle value is your average value. And if you step 1 sigma, sigma is the standard deviation. I guess I could tell you what standard deviation is. It's the difference of the data individual data points from the mean, from the average. Okay, but it's not just that; it's the difference squared. Add them all up, and then take the square root of that. So maybe I'll write that down in a few minutes. Anyway, it's not a big deal. So if you go one standard deviation, you get 34% this way, 34%. That's a total of 68%. If you go 2 standard deviations, then it shows that 95% of the data points will be within 2 standard deviations. Within 3 standard deviations, you get 99.7% of the data points. So what about 5 standard deviations, right? You are essentially at nearly everything, right? It's almost 1. So by 5 standard deviations, it's almost 1. So the point is that they are not allowing data. They're not publishing unless they get an incredibly high signal. Okay, so this is the formula for standard deviation. You take the difference between the individual data points minus the mean, you square it. This is a little thing for statistics if you have small numbers, and then take the square root of that. That's your standard deviation. Okay. Anything interesting? Blah, blah, blah. Okay. Anyways, okay. So, all right, back to the paper. Back to the paper. Okay. So I'm just doing this with the abstract because this is kind of the key information. Okay. So what they did is create these waveforms showing the spiraling black holes, the frequency of the spiraling black holes using conservation of energy, conservation of angular momentum. They created little, kind of animations of what they thought would happen. And then what they do with the gravitational wave observatories, they look for this pattern to emerge, and they sweep a kind of a window across the data, and they look for when the signal matches the waveform. So it's a kind of a weird way of seeing things. It's not like most of the experiments that you've heard about where you just measure something, right? This one is not the same kind of idea. They're looking for a pattern. Now, they are not looking for a single pattern. Okay, so I hope you're taking notes, because every black hole merger with different masses will have a different pattern, a different waveform. So they're not just looking at a single waveform, they're trying to look for a multitude of waveforms simultaneously. So let me see, I don't know if they give you a number, how many different waveforms they're looking at, but they're looking at a whole bunch, not just black hole mergers, they're looking for neutron star mergers and asymmetric mergers, all kinds of things that they've calculated in advance. Okay, so, and then go ahead and write down, this first detection was 410 megaparsecs, write that down, with a Z, a redshift, and I don't think I've really talked to you guys about this. Have I talked about this? Anybody know about Z number? Anybody? Anybody heard of Z?
Not ever before.
Never heard of Z before? Can you write down Z? And I'll tell you what Z means, okay? So from today on, you need to know what Z means. Whenever you come across this in astrophysics, okay? I'm gonna go ahead and just stop for a second. You're gonna write down what Z means, right? What is the Z? Z is related to, it's redshift, right? And this is based on the receding of galaxies. Okay, so this is actually sometimes called the Hubble Redshift. Okay, and what exactly is it? Ready? It's the speed of the galaxy divided by c, right? So if I write down z equals 0.09, then what am I saying? That the speed of receding is 0.09 c. Okay, that's how fast the galaxy is receding. If I write down z equals 0.4 c, then what does that mean? I'm sorry, don't write that, 0.4, sorry. Then v equals 0.4 c. Okay, if I write z equals positive 1.1, How many people are confused? Anybody confused by that?
Yeah.
Does that look right to you?
Everything else has been a fraction so far.
Huh? Yeah. But now you need to know that in fact galaxies can recede faster than the speed of light. If you write down z equals 3, sorry about that. I don't mean to freak you out too much, but in fact, you guys want to be aware that we see galaxies receding faster than the speed of light. And just understand, I know some of you might be like, that's not possible, and I totally understand what you're saying, except you're wrong, and I want to help you understand that. But it's not coming. This is not special relativity, right? Why not? Because special relativity already said that's not allowed, right? That is not allowed. That is not allowed. This is okay. This is okay, right? This is not special relativity, right? This is the expansion of space-time. And because of that, it is general relativity. And it's okay. And it's okay. Okay, it's not against the law. Okay, all right. So yeah, anyways, now you know what Z means. Z tells you how fast that galaxy was receding from us, okay? Or that star or whatever, well, this merger was, okay? So, all right, man, there's a lot of stuff here. Okay, so it's 410 megaparsecs. Maybe you wrote that down, right? Because I think that's kind of interesting. We'll come back to that. 410 megaparsecs. Come back to that. And here we go. In the source frame, okay, do you understand what they're talking about? What does that mean? In the source frame. Help me understand that.
Is that one for the frame of reference of the black hole?
Exactly, but more than that, in the frame of reference of the center of mass of the black hole. Would you write that down, please? So when you see source frame, you know what it means. It's the frame of reference for the center of mass. And so in that system, the two black holes are not moving, right? That's important. They're not moving away from us. They are stationary. We are the ones that are moving, right? So we're trying to understand what is the masses. It's the rest mass, right? Except they're moving very rapidly, it turns out. But anyways, don't worry about that. This is more of a, anyways. Okay, so you write down the two masses, 36. That's kind of cool, 36. You could just write down the best one. But again, I did talk about this before. What does the plus and minus mean? This is the range of uncertainty. And there is a significant uncertainty, right? It's not a small amount. There's a lot of uncertainty. If you can add up 5 and 4, that's 9. That's 1/4 of the value. That's huge. Okay. So what I would let go though is first of all, this is your best fit value, but there is really a range of values which will give you similar results. And so that's what they're trying to show you here. Okay. And 29. So take 36 and 29 and you add them together, and what do you get? You get 65, right? But the final black hole mass is only 62, okay? The best measurement is 62, okay? But a range of uncertainty with 3 solar masses radiated in gravitational waves. So they have quantified the amount of energy that is being radiated away because of this gravitational wave. So all uncertainties define 90% credible intervals. Okay, so they're trying to be as precise as they can. This is the first direct detection of gravitational waves and the first observation of a binary black hole merger. This is a big deal, people. If you don't understand why it's a big deal, how do you see black holes, right? And the answer is we never see black holes, never. We only see the accretion disks, and that means they're feeding. So how could you ever see two black holes merging, right? And the only way you would be able to even possibly see that is if at the same time they were merging, they also happened to be feeding on some nearby star, okay? Or some other system, which just means it's basically going to be really incredibly rare, okay? So this is the only known mechanism that we have now. I mean, it's amazing, right? This is really, truly a work of scientific art. This is absolutely incredible. So I'm trying to make you understand that this is not, I can't make you understand, but I want you to know that my brain is reeling now, just thinking about this. This is something that we've wanted to do for so many years, and finally it's here. Okay, so they do lead you through a little bit of history. They tell you about the first detection of gravitational waves. It was not direct. It was indirect, but anyways, and they do even a little bit more. So 1916, Einstein predicted gravitational waves. He said, if gravity is a manifestation of the curvature of space-time, he showed that you can fit it into the wave equation. And if you can fit it into the wave equation, it means it can make waves, right? And it's kind of like Maxwell figuring out that light is a self-propagating wave. Gravitational waves are self-propagating. They don't need a medium. I mean, the space-time itself becomes the medium. And he found that the blah, 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 don't worry about that. Weak field, this is, I could just tell you, you don't have to know this, but this has to do with far from the source. Okay, this is it makes it a little bit simpler to do the math, right? So when you're close to the source, the field is not weak and it doesn't work. It's not a trivial solution. But when you're far from the source, the equations simplify and they become an approximation. So blah, 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 blah. Okay, I don't know what else. You know, you could read this. It's kind of cool. It's interesting. This is history. I'm not going to ask you to know too much history. I will ask you to know this, though. The discovery of the binary pulsar system by Hulse and Taylor, you need to know them, and subsequent observations by Taylor and Weisberg demonstrated the existence of gravitational waves. So these two originally discovered this really interesting binary pulsars. So have we talked about pulsars? Do you guys know what a pulsar is?
Was it a rotating neutron star with jets?
Right, absolutely. Okay, so I heard from Lonnie. Does anybody else want to step in, chime in? Can you tell me if you know what a pulsar is? Because otherwise, I feel like I should just pause for a moment. Leona, do you know what a pulsar is?
Yeah, I remember learning about them in astronomy, but I'm not sure if you've talked much about
I
them.
don't. Okay, yeah, I don't think we did either. So maybe I could just pause for a moment and talk about that. So what is a pulsar? So we've talked about black holes, and I think did we talk about how black holes form? I feel like I don't know if I ever really talked about it with you guys in this. I feel like I must have. No?
I think you briefly did, yeah.
I don't know. Brandon, can you help me out here? Did I talk about how black holes form?
I mean, didn't we just briefly touch on like if a bunch of mass gets dense enough?
Right. Okay.
But I guess we never really talked about how it gets that dense.
Shoot. Okay. Well, I think it would be kind of important for a black holes class to talk about how black hole forms, right? So maybe I could just pause what I'm doing and just make sure that I fill this little gap. Okay. So a star lives and it uses its fuel in the core, mainly in the core at first, to fuse atoms together. And the fusion of the atoms leads to something new. And that new material we call the ash of the fusion reaction. And the new material, if you were to weigh it or measure the mass, the interesting thing is what you put in right over here in this hand is what I put in. Actually, let's go this way. I don't know whichever one. It doesn't matter. Okay, let's do this one. This is what I put in. Okay, I put in stuff. and then I get stuff, right? And if this was ordinary, baking cookies, then the masses would be the same, right? Ordinary reality, ordinary life, okay? But in stars and nuclear fusion, what you put in does not have the same mass as what you get out. And in fact, what you put in is more massive than what you get out. And that's an important idea, because if that wasn't true, then they wouldn't work. It has to be that the mass of the product, the mass of what you get, is a little bit smaller in order that that mass can be converted into energy, which supports the star. So the formula, remember, E equals mc squared. The little bit of matter that is converted into energy is going to be what keeps the star from collapsing. So a star forms when a supernova or some other shock wave goes through a cloud of gas and makes a little tiny seed, a slightly compressed area. And I don't really know how that happens. I just know that it happens, probably an interference pattern of some kind. But you get a little cluster, a little tiny place that's different than the rest of the cloud. And because of that, it will actually start to collapse. So it collapses matter. The matter comes together. It gets hotter as it collapses because of conservation of energy, and forms what we call a protostar at first, and then eventually a star. So the fusion process begins, and the idea is that a star is alive as long as it's able to fuse elements and get energy out. And so the energy goes into making what is called radiation pressure. And so actually, I guess because I haven't talked about it before, let's make sure you understand that. If you took astronomy already, that's great, you know this, but for those of you who didn't, a living star is in equilibrium. And what does that mean? Well, the forces are balanced, right? So we have an inward force, which is the force of gravity. Gravity is caused it to form in the first place. All right, that's gravity pushing in. But if it doesn't keep collapsing, the reason is that there's another force that is pushing out. And it is, and we have three choices. We have bigger, smaller, or equal. And hopefully you recognize from the word equilibrium that this outward force is exactly the same strength as the inward force of gravity. And this force is called radiation pressure. And so where does the radiation pressure come from? Well, it comes from nuclear fusion. Okay, so nuclear fusion. All stars begin by fusing hydrogen, right? Actually, it's really hot, so it's not hydrogen atoms, they're hydrogen ions, which is essentially a proton. That's what it is, a bunch of protons, right? And so you fuse hydrogen, and hydrogen fuses, we're not going to do an in-depth study here, we're just trying to get an idea, fuses into helium. That's what it forms. So the way you do it is you take 4 hydrogen ions, and that makes a single helium ion. Okay, so this turns out to be the reaction. Okay, so now if you weigh or take the mass of this side, it is not the same as the mass of this side. This is greater mass. So what happened to the missing matter? It was converted into energy, right? You get energy coming out, and the E was E equals mc squared. Okay, that's where the E comes from. The missing matter turns into energy. This is what's creating the radiation pressure and pushing against gravity. So eventually you run out of fuel, right? Eventually you run out of fuel. I'm not telling you the whole story, but anyway, we're gonna do the simplified story. You run out of fuel. You run out of fuel, and the star collapses. So gravity wins, okay? But it turns out that whatever you're left with at the very end, when you run out of fuel, whatever you're left with at the very end determines what you end up becoming, right? So if you don't have too much mass left over when you're done, if your mass is less than 1.4 solar masses, That's masses of the sun. Then you become a white dwarf. I really didn't talk about all this. Okay, this is kind of important stuff. A white dwarf is a it's about Earth size, right? Earth size. Earth size, you know, dead star, right? It's a dead star. And the idea is that these white dwarfs are not collapsing. There's still a force of gravity. They're really tiny. Actually, they're the size of the Earth. There's still a force of gravity. But this time, there's no more radiation pressure because they've collapsed, right? They are actually made almost entirely, make a little note, of carbon and oxygen. Carbon and oxygen, that's the leftover stuff. So it turns out I left out a couple details. The hydrogen fused to helium, then the helium fuses to form carbon and oxygen, and then it runs out of fuel. It collapses, okay? It forms a white dwarf. So what is the force that stops gravity, right? Gravity is still trying to pull it in, but this time it's not radiation pressure, it's got to be something else. And so it turns out these are atoms, right? This is made up of atoms of carbon and oxygen. And those atoms have electrons. It turns out there's lots of electrons whizzing around in here, and they are actually not on the atoms. In fact, they are free electrons. And those free electrons are going to be holding up this object and preventing it from collapsing. So the name for this force inside that stops gravity is called the electron degeneracy pressure. Okay, electron degeneracy pressure. So that stops gravity from collapsing it any further. So this number, it turns out, is a theoretical number that was determined by an Indian physicist, astrophysicist, by the name of Subramaniam Chandrasekhar. So can you please write that down? Chandrasekhar limit. And it turns out this is the largest mass that a white dwarf can be. And so why would this be the largest mass? Well, what happens when you have more mass? As you increase the mass, you increase the amount of gravitational force. And at some point, the electron degeneracy pressure is just not strong enough. And so this cannot exist. It cannot be a white dwarf anymore. So if you had more mass than this, then this could never form. So we're not going to talk about it. In fact, what happens sometimes is white dwarfs gain a little bit of extra mass and go above this limit and become an exploding white dwarf. Actually, we could write that down. Let's write that down. An exploding white dwarf. Why did it explode? Well, it turns out if you collapse it, all that material that was just sitting there as atoms explodes all at once. It's called a type 1A supernova. Supernova. Okay. So you have a white dwarf that explodes. Okay. So that's interesting. That happens sometimes. And the reason it exploded, it went above 1.4 solar masses. That's an interesting story. Okay, but we're not going to go anymore. Now, if you're a bigger stars, that they actually will do something a little bit different. They won't go to carbon and oxygen. It turns out they will fuse all the way to iron, which is the element Fe. I didn't talk about any of this stuff with you guys, so this is a big hole I'm trying to fill right now. I should have told you guys about some of this. But they go all the way to iron. So they keep making energy. Actually, let's just look at a quick picture for you just so you can see something that this is called so large mass stars. They're going to do something a little different. They're going to go all the way to iron. Okay, and here we go. That's the picture I'm looking for. Okay, so if you looked at a very large mass star, at the very end of its life, it would look something like this. So what has happened is the star started with just hydrogen and helium. In fact, mostly hydrogen, 3/4 hydrogen, 1/4 helium. And remember, that's the ratio that was set up at the beginning of the universe, the Big Bang, right? The beginning of everything. The elements hydrogen and helium were present. So all stars begin with hydrogen as their fuel. It's the easiest fuel to fuse. And then as they run out of hydrogen, the hydrogen turns into helium, the helium turns into carbon and neon and oxygen and silicon. You finally make iron. This is what it looks like. It looks like, sometimes people call it the onion layer, right? Onion skin, sorry. So you have this iron inert in the core, it's not fusing, and you have these other layers that are burning to make energy. And this is actually called a red supergiant right now. A red supergiant is a stage just before the star is going to finally explode. But let's take a look at this iron core here. The iron is not fusing because when it begins to fuse, the star will instantly die, okay? And I guess I'm telling you, you need to understand what's going to happen. Why is that? Why is the iron the end? And the answer has to do with the efficiency of fusion. I don't see it here. Okay, hold on. I don't see it. I don't see it. Iron. Where is it? Come on. Okay, iron. Okay, so it actually has to do with the binding energy. Binding energy. Iron, let's put that in. Nuclear binding energy, let's try that. Nuclear binding energy. I'm looking for an element. There we go. Okay, here we go. So this is the nuclear binding energy curve. And the idea is that the number of a nucleon is a proton or neutron inside of the nucleus. And the idea is when the atoms are very small, the amount of binding energy. So what's binding energy, by the way? The energy associated with the nucleus being together, right? Binding energy. The average binding energy per nucleon is going up, 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 up. But if you look right here, Fe is the highest, right? Actually, there's a couple of elements right here that are very close together. Fe happens to be the most stable of them. Okay, so anyways, don't worry too much. But anyways, the iron core is somehow more stable. So let me explain why this is important. If I take the hydrogen and I make helium, which is right here, by the way, you can see it went up amazingly high in terms of the binding energy. Well, this is actually a good thing for a star because when you make something with a higher binding energy per nucleon, it's somehow more efficient. And because it's more efficient, it has less mass. And therefore, it releases energy when it forms helium because you've made something that's more efficient. Now you can see if I tried to make lithium, that actually is less efficient. But it turns out that's not going to happen. You're not going to make lithium from helium because it's less efficient. It would require energy. It would absorb energy. But you can certainly make carbon and oxygen because they are more efficient. And so making carbon releases energy, making oxygen releases energy, making neon releases, etc., right? But something happens when you're at iron. If you try to use iron to fuse and make a heavier element, you're going to end up down here, which is less efficient. So the key concept that you want to understand is fusing Fe absorbs energy. So the moment that a star begins to fuse its iron, it dies, and it's tremendously energetic. It's tremendously energetic. It's called a type 2 supernova. So then the last stage of a star's life is this explosion. And you might think, well, it's done, right? It's dead. But it turns out there's actually 2 possible end states that it can have, depending on the amount of mass, right? So it can actually form 2 different things. One of them is this iron core can collapse. And if it's greater than 1.4 solar masses, then it cannot exist as atoms anymore. And so something really interesting happens. If it's greater than 1.4 solar masses, And we think that the number, I don't know the top number here exactly, but I'll put down the best number I have right now. It's about 2.7 solar masses. If you're in this range, then something interesting happens. The electrons are not strong enough to stop gravity. And so the electrons merge, they enter the nucleus. And what do they do there? They find protons. And what happens then? They merge and form neutrons. And so in this situation, this scenario where the iron core that's left over, this is our iron core, Fe core that's left over at the very end, after the explosion, the iron core left over, if it's between this and this, we know that it can't form a white dwarf because it's above 1.4, but it forms something called a neutron star. So what is that? It's a ball of neutrons, right? I mean, the simplistic idea. This is good enough for us right now. The ball of neutrons. How big is it? It's the size of a small city, like 10 miles, about 20 kilometers across, right? This thing is tiny, right? But it turns out at this point, it stops collapsing, even though the gravitational field is incredibly strong. There is something that is just as strong as gravity. So what's the name of the force that stops gravity from collapsing it any further? And it turns out it's the strength of the neutrons themselves. And so the force is called neutron degeneracy pressure. So this stops gravity from collapsing it any further. So you get this thing called the neutron star. By the way, remember the conservation of angular momentum? If a star was rotating when it started, and then you collapse it down to this tiny little ball, what's going to happen? It's going to rotate incredibly fast. And so you might get, in most situations, almost all situations, a rapidly rotating, really fast rotating neutron star. And it's gonna have a powerful magnetic field associated with it. And as a result of that, you're gonna get these jets coming out of it. And so the jets are gonna sweep around in different directions because they're actually not perfectly aligned. That's a weird thing, by the way. I can't actually explain that very well, but they're not always perfectly aligned. And as a result, they sweep around and what we call a pulsar. So a neutron star and what we saw, pulsar, is a rapidly rotating version. Rapidly rotating neutron star is called a pulsar. Okay, so let me actually, maybe I just show you a quick little lighthouse model of a pulsar. Okay, so images, I guess. Yeah, something like that. Okay. So if you take a look right here, I'm just on and looking for something. That's kind of a cool looking picture, right? You got a neutron star and it's rotating, but the axis of rotation and the magnetic field are not necessarily exactly the same. And there are these jets of material that come out of them. And if this happens to be, if the Earth is in one of these directions, here or here, then we would see it, right? We would be able to see those jets. Okay. How about this one? That looks cool. Let's see what that is. We got an animation. I don't know animation. Oh yeah, animation. Cool. I like animation. Okay. So if the jet is pointed at us, we get a flash. And actually, the first pulsars that were detected by radio astronomers, and they got a burst of radio frequency. That's kind of funny. And it repeated in this kind of regular fashion in a way that was like just so impossible. And so some of you guys might know, in the very first pulsars that were detected, were radio astronomers detected them. Who remembers the name that they give them? There were these regular bursts of radio frequency that were actually so regular that they thought for sure that they were human made. But when they looked carefully, they discovered that they were nowhere near the Earth. They did parallax measurements, actually. And Lonnie, what are they called? You remember?
LGM.
They're called LGM. That was it was like a temporary name, but when they first detected them, they didn't want to publish the results because they really believed that it was human, maybe one of the first satellites or something like that. This is the early 60s. And in fact, they thought maybe they were LGM. What's the LGM stand for?
Little green.
Little green men.
Little green men, aliens, right? Aliens were trying to talk to us. And it turns out they weren't aliens. They were just these flashes that come from a neutron star. So it is called a pulsar, okay? So, and then let's finish our story because we're almost there. How do you make a black hole? You put too much mass, right? If you're above 2.7 solar masses, right, left over, I have to move my dot down, okay? What can stop gravity, right? Well, so the electrons were not strong enough. And now it turns out the neutrons have limiting strength too. This number is just from last year, by the way. I didn't know this was the number 2.7 until last year, and I will tell you why. It has to do with what some of the something that you were learning about the last couple of days. But this number is brand new for me. About last year sometime, this number showed up. Before I used to use 3, but this number is close to 3, right? It's pretty close to 3. It's probably a little bit lower. Maybe it's 2.5 or 2.4. I don't know what it is, but this is the best number I have right now. What happens if the leftover mass in your core is above 2.7 solar masses? The neutrons can't stop gravity. So what can? And the answer is nothing can stop gravity, right? So what do you get? You get this collapse down to a mathematical point. You get a black hole. Okay, I'm not going to talk about the singularity today. I don't want to talk about it. But anyways, nothing can stop gravity, okay? Unless gravity is quantum, in which case what will stop it is the Planck length, and that's fine. I'm good. But you get a black hole. So the black hole forms because there's just too much matter for anything to stop gravity, right? The gravitational field is just too strong. And so we know about the mathematics behind the event horizon of the black hole. So I think I'm okay now. But now let's go back to our paper and see if we can understand. Actually, I can just sketch it out for you. But the idea was I have these pulsars, and they have their jets, right? And somehow I'm able to see them both. That's kind of cool, which means that they happen to be sweeping, you know, towards the Earth, but they're orbiting a common center of mass. Right, they're orbiting a common center of mass, and these ones are so close together. They're really effectively distorting space-time, and they are sending away these gravitational waves, right? So what happens if you are creating gravitational waves? Well, that's energy. And as a result of that, the energy of this system must be going down. But again, it has to continue to preserve the angular momentum. So what happens is these rotate faster around their center of mass, right? And so this is what they actually observed. Okay, so the paper refers to this observation, and this is actually what the Nobel Prize was awarded for. Okay, so this is actually what they watched. They watched the discovery of a binary pulsar system, PSR 1913, blah, 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 B 1913. And they showed that the change in the period was exactly based on the emission of gravitational waves. Okay, so I'm paraphrasing. Okay, so yeah, then you could read this, and it's a little bit of history. When did they begin? Okay, so this is kind of an important thing. By the early 2000s, a set of initial detectors was completed. So remember, I said 20 years, but in fact, it looks like they only started building this in the early 2000s. The TAMA 300 in Japan, GEO 600 in Germany, LIGO in the United States, and Virgo in Italy. So combinations of the detectors made observations from 2002 to 2011 and declared nothing, okay? So the sensitivity was not there. They could not do it. And then in 2015, there was a major upgrade in the equipment of LIGO. And it's 1 month after the installation of the equipment, and they finally got it started. They were actually just testing it. And this is when they detected their first gravitational wave. Okay, so September, I thought it was September 15th, September 14th. Oh, I'm getting confused. September 14th, 2015 was the first gravitational wave. So you want to take a look right here. We have 2 different sites, Hanford and Livingston. These are the 2 sites. And you can see the real data is messy, and that's fine. And then what they did is they tried to show that these in fact were the same signal. That's important, right? If it was a different signal, then it wouldn't be a real gravitational wave. The other thing to realize is these signals were not simultaneous. There was a small delay. And the reason is that the gravitational wave hit this place or this place first. I don't know which is which, but the idea is that they actually detected the wave in one location slightly before the other location. And this tells you a little, detail about the direction, but it's not enough to really tell you the true direction of the wave. Okay, so as you read through this paper, I didn't really expect you to get too much, maybe just to look, at this picture. Here's a frequency thing. What do you see happening to the frequency? You see how it's ramping up, right? This is the idea of the in spiral. This is the in spiral of the black holes coming together. And a similar thing. Okay, so here is an in spiral. The center part is the merger, and the final little oscillations are called the ring down. You need to know those words. Okay, so in spiral, as they approach each other, they're increasing frequency because they're getting faster and faster in their orbit around the common center of mass. The merger is a little messy. This vibrations are pretty large amplitude vibrations in the gravitational wave. And then the ring down is the last little kind of waves that you see, and then it's silent. Okay, so then it's silence, right? The sound of silence. Okay, so this is a big deal. All right, so as they get closer together, they move faster and faster. Okay, cool. And look at how they measure this. Oh, this is just kind of cool. Again, you're not researchers, you don't have to know this, but look at how they measure it in terms of the Schwarzschild radius, right? The Schwarzschild radius of the new black hole, Schwarzschild. Isn't that crazy? Oh my God, that's so awesome. That is awesome. No, that's wrong. What the heck? Black hole separation. Oh, okay, I'm misreading this. Black hole separation. Oh, yeah. Black hole separation goes down. The velocity. Okay, so you have to read it in 2 different ways, right? Read this graph using this one, and read this graph using this one, right? So you have to read separate sides. This should be in black and this should be in green, but they didn't show you that. Oh man, isn't that pretty? Okay, so then they talk about the detectors. Okay, so here are the locations. What do you notice about the orientation? There's 2 arms, and each arm is 90 degrees to the other arm. And that's actually kind of important because that allows you to decompose the wave into 2 pieces and talk about the pieces independently. And then these arms are not the same orientation. That's on purpose. That was purposeful. It lets them probe slightly different directions. Okay. And they're also, the Earth is curved, so they're really 3-dimensionally in different directions too. Okay, so the essence of it is right here. This is called an interferometer. So you need to know what an interferometer does, right? What does it do? You have a source of light, the laser here, an intense beam of light. And actually part of the upgrade was to give a more powerful laser, right? So what was the upgrade? More powerful laser and better mirrors, and then a better detector. Okay, so all 3 things, right? So better laser, better mirrors. What's better about it? Maybe tell me how you make a mirror better. How do you make a mirror better? I'm trying to ask you guys a question.
Having a bigger one.
A bigger one? A bigger one is a good idea. It turns out it didn't get bigger though. So how else could you make it bigger? Better. What would make a mirror better? What's a mirror do? What does a mirror do? What's the function of a mirror?
To reflect light.
Okay, very good. So how could you make a mirror better?
Curving it?
Huh?
Curving the mirror?
Okay, that's a good idea. So you're trying to trap more light. So it turns out curving makes an effect that they didn't want. It's not a bad thing, but it's great for like a telescope, right? To curve the mirror because then it focuses light. But they really didn't want that kind of an extra added element. In fact, they wanted a super flat mirror. So one of the things that they did better is the mirror that they put in 2015 was even flatter than the mirror that had been there before. And the flatness of the mirror led to, so the reflection is kind of actually a more mathematically simple reflection because it's so flat. You don't get noise, as much noise. So it reduced the amount of noise. And then the other thing is the amount of light that's reflected was also increased. They made a better mirror. It reflected more light, right? So, I mean, technologically, you want to understand why did we not detect gravitational waves before this? We had, you know, big mirrors, but the quality was not high enough to be able to perceive this. It was really this step that led to the increase in sensitivity because the signal to noise ratio increased that allowed them to see it. Now you should also know that they've since then improved them even more, right? They've made them even more sensitive. And that was just, they paused the Gravitational Waves Observatory in 2017 to do another upgrade. Okay, so they made better mirrors, blah, blah. Better laser, more powerful, more coherent, blah, blah, blah. Okay, but the beam is split. One beam goes this way, this one beam goes this way. And they're supposed to go the exact same distance, 4 kilometers. Remember why it has to be 4 kilometers, right? Why does it have to be 4 kilometers? Because the strain is 10 to the minus 21st, right? You can't measure it if you don't have a long enough arm. If this arm is not big enough, you can't detect such a small change, delta L, in the length of the arm. But that is literally what's happening. The gravitational wave comes through and this distance changes slightly. And because of that, the light waves that travel along here will do a different number of oscillations depending on if they go this way or this way. So when we bring them back together, they will interfere. And the interference pattern is what you're trying to read. Not the individual wave, but the interference pattern. It lets you read a fraction of a wave. Okay, so this is a lot of cool stuff. It's just so crazy how amazing this is. I mean, they talk about like what are the things they talk about? The output photodetector records these differential cavity length variable, blah, blah, blah. Gravitational waves propagate, blah, 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 location oriented. The instrument noise for each detector near the time of the, okay. There's just so much stuff that can go into this. The mechanism for hanging I mean, this is just crazy. I shouldn't even, I mean, I don't know that you're going to understand everything here, but take a look right here. Let's just, interferometry, seismic noise, right? It feels the sloshing of the ocean, right? Hundreds of miles away. I mean, it's just crazy how careful this thing is actually measuring vibration. But thermal noise is minimized by using low mechanical loss materials in the test masses and their suspension. They hang the mirror from these 40 kilograms fused silica substrate, blah, 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 blah. Okay, anyway, there's all these crazy things to dampen vibrations and blah, 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 blah. Okay, it's just amazing. So that's all. I think that's about it. There's too much other stuff in here. You guys don't have to understand all that stuff. Conclusion, let's read the conclusion. The LIGO detectors have observed gravitational waves from the merger of 2 stellar mass black holes. The detected waveforms match the predictions of general relativity for the in-spiral, merger, and ring down. These observations demonstrate the existence of binary stellar mass black hole systems. This is the first direct detection of gravitational wave and the first observation of binary black hole mergers. So just to go to the first page again, you don't see the people. Where are all the people? The full author list is given at the end of the article. Okay, here. Okay, right. You guys want to understand, right? How many people are involved? How many people are involved in this? Oh my goodness, right? Here it is, the list of authors, right? This is science today, right? This is incredibly complicated. Look at all the people that had to be a part of that, right? This is an enormous collaboration. And actually it's very exciting that this happened, right? This is not just a story of difficult science, but story of collaborative science, right? This is a global scientific community that is working together. Why can't we do that in everything that we do? Because that would make our world too good. Anyways, pretty exciting stuff. Okay, so we looked at the paper. I spent a lot of time on that paper. Wow, almost the whole time was on that paper. I guess I talked about black holes too. So you watched also the kilonova video. Actually, I'm going to talk about the kilonova on Monday, I think, because it's just too rich. I don't want to talk about it today. What I'd like to share with you is some news that I just read, and I think it's pretty exciting. So the mergers that we've been hearing about, just so you're aware, the kilonova is a whole nother beast, by the way, and it's going to be on your final somehow, right? I actually, an essay, or not really any calculations, so an essay about kilonova. You better know what a kilonova is. I find it so incredibly rich and beautiful. You need to understand that. But something was announced just recently, a couple days ago. And this was a merger, another LIGO detection. Actually, I don't want to do that, sorry. I wanted to show you here. Let's go over here. Okay, so I'm going to put, instead of being the same size, this is the first time asymmetric. Black hole merger. So up until now, the mergers that we've been seeing have been symmetric, meaning they're about the same mass. But this is, there's actually a video. Let's watch that. I want to see that. Black hole merger, Max Planck. These are excellent places. These are very respected theoretical places. Okay, so here we see non-symmetric masses. And is there sound? No, no sound. Doesn't matter. And anyways, that's kind of interesting. But these have been modeled. And for the first time, we found them, right? So this is one of the things that they see. So what's going on right now? The black holes are getting closer together. What do you call that?
The in spiral.
The in spiral, right? And then you're going to see, look at the waveform down along the bottom, right? Look at the waveform down along the bottom. You see these are milliseconds. It's happening very quickly. Oh my gosh, it's beautiful. Wow, artistically, gosh, that is just gorgeous. Isn't that amazing? Wow. Oh, wow. Look at that. Oh, that is amazing. Wow. Okay. Something crazy is here. Movie frozen. Okay. The merger. Oh, look at all the little ripples. Okay, you get this oblong shaped object, and there it goes. It's gone. Okay. So the merger and the ring down is pretty fast, right? There's not much of a signal there, right? Oh my God, that is really quite beautiful. Gosh, I will ask you one or two questions on that. Anyways, this was just announced a couple days ago, which is kind of amazing. Let's see. If you go to the website that I mentioned, this is the LIGO website. You probably looked at that. There's some really beautiful videos. And actually, this is a video, again, showing the merger of two similar sized objects, right? Similar mass objects. Doesn't matter if they're neutron stars or black holes, you get a similar kind of picture, but with different masses, it will take a different amount of time, right? Different amount of time, different speeds of in spiral. But it's a little different picture than we saw before. So now that, actually, what is that supposed to be? This is supposed to be two neutron stars. Okay, so did you see the light when they came together? That's a little bit different from black hole mergers, because black hole mergers don't emit any light, but neutron star mergers can emit light. Okay, they do emit light actually, and that's the kilonova. Why detect them? Sources and types of gravitational waves. Okay. Oh, here's a black hole merger. Okay, computer simulation. Oh, there's no sound anyway. This is actually showing you what it might look like from to an observer nearby, right? So what's the effect that you guys are seeing around the edge? Remember what that's called?
Is that Einstein's gravitational lensing?
That's gravitational lensing that we're seeing, right? So you can see behind the black hole. Everything behind the black hole is being shown because the light is bending around the event horizon, actually about 1.5 times the short field radius, the light around that. Oh, just around the mass, whatever. So yeah, you wouldn't see much more if you were close. And then it would just get quiet and you would see a single ring around there. Okay, that's kind of fun, neat. And this is the chirp. You guys have probably, I think I played this already, but anyways, let's play it again. Okay, so that's the chirp. And then this is so could you guys actually hear that? Could you guys actually hear that?
The
It's
volume
very-
is kind of low, but
Yeah, you might have to actually go hear that. Go listen to that if you can. But it's very faint, and I think that's a really important idea to understand. There's so much noise from the surrounding universe, right? That when you try to hear that little chirp, you're trying to hear it through this multitude of sounds that are all around us. Okay, so that's about all I can do today. But I guess I want to make sure you understand, where do gravitational waves come from? Just to finish it off, where do they come from?
They come from the energy that is released when two objects of mass are falling towards each other.
Okay, that's one way that we see that they're created. And these are really dramatic and something that we can characterize. We can talk about them and we can model it. We have models of how the black holes will merge, how a neutron star will merge. And because we have those models, we can make predictions about what they should look like or feel like, really, because that's what's going on, right? We're feeling a vibration of space-time through these interferometer system, and we're feeling that happen. And when you watch the kilonova video, there's a great little animation showing the Earth as it's being squished. That's an exaggeration, of course, but because actually we're talking about something as small as a proton, as small as a single individual proton. All right, let's see what else. Oh, so one source is when you have mergers, right? But it turns out that we also believe that there should be lots of gravitational waves bounce, around from the very beginning of the universe. So just be aware that the future of gravitational wave astronomy is not just for these merger events. Those are cool. But the future is to detect the underlying background noise and be able to say something about what that means about the early universe, right? We can't see the light from before 300,000 years, right? That light does not exist anymore. It was absorbed. It could never get through the universe, right? We only see light from the period after the electrons coalesce, joined atoms. When we formed neutral atoms, we finally had a state of the universe where it was clear and we could see the light. But gravitational waves from the very beginning are there, and they're bouncing around the universe somehow. I don't know how they're bouncing. That's the confusing point for me. How do gravitational waves do? Do they diffract? Ask somebody that. If you get a hold of a PhD or in gravitational wave theory, ask them about that. Do they diffract? Do they interfere? Maybe they're part of the story. They must interfere. Gravitational waves must interfere. Okay, so I'm going to stop for today. Thank you guys for coming. And I will be making some questions up based on the material. It's really, we kind of went into a little detail on that paper. And then you learned some key words. So I guess my quiz today will be mainly on that. And then we did talk about how black holes form. So I'll throw in a couple of questions on that as well. All right, well, thank you guys very much. And I'll see you guys next week. Thank you.
I should have a question real quick.
Okay, go ahead.
So on page 162 of the book, Stephen Hawking says there is 10 or 26 dimensions for string theory, but you said
that's not, it's kind of a little behind the times. So you guys, that book was written before the big string theory conference that Ed Witten proposed M theory. So we did find, so that we were looking last class actually for this. So right now you should say 11 dimensions for the M theory, and that happens to be the best theory so far. But the original string theories had up to 26 dimensions. That's true. So Hawking was talking about that. That was one of the original versions. But now it turns out, I thought it was 22, but in fact it's not. It's not. Yeah. So don't go with 26 anymore. Yeah, Hawking talks about that 10 and then 26. But in fact, right now with M theory, it's going to be 11.
Okay. Thank you.
Yeah. I mean, after 11, what is it anyways, right? 11 is even enough.
Yeah.
Even see the 11. So, but actually we talked last time about where those 11 are, at least maybe, some of the ideas, right? That they're very, very tiny coiled dimensions, maybe rotations, maybe
vibration,
different things that we can't perceive, right? We have they're either too small or we don't even have the technology to probe what's going on. And there may be even other things that we don't know about, right? We believe that the standard model is complete, that it explains every particle of matter, but we already know that it doesn't include gravity. So if these things really are together, then it is an incomplete theory. So there's room for maybe even other properties of matter that we're not aware of. And those would represent the dimensionality that we can't see yet. Okay, so thank you guys very much. All right, so let's see, what are we going to do for next time? I did mention one thing. Well, I really want to talk about kilonovas next time. Actually, since I want to give you guys something to do, I'll give you the quiz, of course, for today's participation. But I'm going to post a link for another Wikipedia site that I'd like you to look over so that we can bring that into our conversation. This is actually the reason why kilonovas are so interesting to me. And it's a topic called stellar nucleosynthesis. Okay, so I'll ask you to look that site over to try to get an idea, just a general idea. This is actually a big story. Where does the periodic table come from? Where do the elements on the periodic table come from? And honestly, I did not understand this up until a few years ago. I can't say I understand it, but I do understand a little bit better now that we've seen the first kilonova. That is actually a mechanism for generating the elements on the periodic table. So neutron stars colliding, we're going to learn, is an exciting way to make elements. Hopefully you already watched the video, so you know about that. But anyways, I'll ask you to read that website or look it over, and with the idea that on Monday we can talk a little more deeply about kilonovas and why they happen to represent like a really exciting time for astronomy, astrophysics, okay, and cosmology. All right, thank you guys. All right, have a good day. See you later.
Thanks, Professor. You too.
Thank you.
Thank you.
Bye. Leona, did you get that? You got the questionnaire, right?
Yeah, I did.